Hello everyone, welcome to this session on synthesis and RTL coding. So we have been seeing about different optimization that happens in synthesis. So we are now going to see one very interesting optimization that is going to happen. Let us first look at the RTL code. The RTL files we are going to use are present in the same folder Verilog files. These are the two modules we are going to see, mult2 and mult8. mult_2.v, mult_8.v. These are the two RTL files we'll be using for this lab. Okay, let us first try to understand what exactly we are trying to do here. So if I look at the Verilog code, what is the Verilog code trying to do? It is saying that it is accepting a 3-bit input called A. It's accepting a 3-bit input called A. This is a 3-bit input. And it is generating, it's accepting the 3-bit input, so 2:0. And it is generating a 4-bit output called Y. And this Y, the relation between Y and this Y is equal to 2 into A. This is the relationship. So first, let us look at this relationship for an instance. So what are the possible inputs? Let me write the truth table here. These are the bits. So I can get what 000, 001, 010, 011, 100, 101, 110, 111. So these are the possible. So 0 multiplied by 2 is going to be 0. 1 multiplied by 2 is going to be 2. 2 multiplied by 2 is going to be 4. 3 multiplied by 2 is going to be 6. 4 multiplied by 2 is going to be 8. 5 multiplied by 2 is going to be 10. This 6 multiplied by 2 is going to be 12. This 7 wait. 12 is this, correct? And 7 multiplied by 14 is going to be 7 multiplied by 2 is going to be 14. Now if you see the beauty here, if you see whatever we have written here, exactly the same numbers are coming here. The last bit is appended with zeros, correct? So this is our observation, okay? So whatever number we have written here, the same number is present here everywhere. So multiplying by 2, a number multiplied by 2, the answer is nothing but the number A appended with a 0. This is going to be the answer. So ideally speaking, I don't need any hardware for doing this. So you give me a number. See, for example, you give me A. A is a 2:0, correct? So there's a 3 wire for this. And I need to generate Y. Y is a 4-bit signal. How do I generate this? Make this as Y of 3. Make this as Y of 2. Make this as Y of 1. This is my A of 2, A of 1, A index 0, and Y index 0 is grounded. I don't need any hardware for this. See, initially we thought when we saw this multiplication, we thought that we need a multiplier, right? But multiplying by 2 or powers of 2 is going to be just shifting. Similarly, let us look at that. If I multiply by 4, take any number. Let's say, for example, I take 5. I multiply 5 by 4. What will be the answer? This is going to be the answer. This is 20. This is 5 multiplied by 4 is going to be 20. So this is nothing but appending 2 zeros to the number. You can check. This is going to be 2 power 0, 0, 2 power 1, which is 0, 2 power 2, which is 4, 2 power 3, 0, 2 power 4, 16. I'm doing the binary to decimal conversion. The answer is indeed 20. Similarly, if I take any number and multiply it by 8, what I need to do? I need to append 3 zeros. That's it. Whatever is the number, append 3 zeros at the end. That is what is multiplying by 8. So this is what is our understanding. Let us see in the lab actually what happens if we take it through the synthesis. So if you see here, I have effectively multiplied it by 2. So let us look at mult2. What happens if I synthesize? So we launch uses. So read liberty -lib / mylib lib sky130 read verilog. Our file is mult2, correct? One second, where am I? Okay, read underscore verilog mult_2 mult_2.v. Yeah. Now I say synth-top mult2. I don't expect any hardware for this, correct? So let's see. Whenever we execute the synth-top, we need to be very careful in observing what is the cell profile, correct? This is what we have been seeing so far. So please note, there have been no memories, no processors, no cells inferred. The number of cells inferred is 0. Okay. Now I'm going to do abc-liberty. It will say not needed to do at all. abc-liberty / mylib lib. It will say, see, don't call abc when there is nothing to map because there is no standard cell at all. So when you do show, see, this is just A appended with one tick B0. This is our Y. This is what we expected, correct? And that the same thing we are getting. This is what we expected here, correct? If you see here, the number A appended with 0, correct? That's what we expected. And that's the same thing we are getting here. We expected number A appended with 0, correct? This is what we expected. And that's the same thing we are getting. Correct? So this proves our understanding is correct. So there is no need for any hardware here. Okay. Now let us look at another special case. By the way, these are special cases, okay?